Hello there,
Now that we've
and welcome to
established
Just
that
About
Pangea
Earth,
wasn't the
where
first time
curiosity
Earth
gets
had
cozy
gathered
and
most of
science
its
takes
lands
the
into a
scenic route
single
to
chunk
slumber.
of continent.
Tonight's journey
Let's
is
get to
going to
know
take
those
us
earlier
way, way
supercontinents
back
a
in
little
time.
better,
We're going
beginning with
farther back than the
Rodinia,
dinosaurs,
which means homeland in
farther
Russian.
back than the lush,
Rodinia
steamy
was a big
jungles they
deal.
roamed.
It was the
We're
first
even
time
going
that a
farther
lot of
back
the
than the mighty
continents we know today
supercontinent called
got together
Pangea,
in a lasting
that
way.
giant puzzle piece of
Eventually,
land many
they
of
would
us learned
split
about in
apart
school.
and reform,
But before
but
we
they
start our
spent a
travels
significant
through those
amount of
ancient,
time
forgotten
glued together
landscapes,
during the
I'd
Proterozoic
like to ask you
eon,
something
which
simple,
lasted from
something
about
to ground us
2.5
in the
billion
here
to
and now.
541
Where are
million
you
years
listening
ago.
from?
That's
Maybe
right,
it's late at
billion.
night,
Let that
and you're
sink
curled
in
up
for a
under a warm
second.
blanket.
It's a number
The
humans
world
don't
outside
usually
quiet
deal
and
with.
still.
We measure our lives
Maybe
in
it's a
days and
peaceful,
weeks,
early
and maybe
morning,
if we're feeling
just you and your
adventurous,
first cup of
years.
tea or
But the
coffee.
world spun
Or maybe
on
you've
for
just
more than
stumbled upon this in the
1.5
middle of a
billion
hectic
years before
day,
we showed up.
looking for a
And that
small
world
island
was
of
made up
calm
of
in a
spinning
sea of
plates of
noise.
rock moving on
Wherever you
top of
are,
a molten layer
whenever
of
it
the
is,
earth called the
you and
mantle.
I are about to
It's
take a
called the
quiet
theory
walk
of
through
plate
Earth's deep
tectonics,
past.
and it's a pretty cool
There's something
explanation
fitting
for
about
how we
that, isn't
got
there?
here. During
Here
the
we are, scattered
Proterozoic,
across
the
different
African,
places, living
North
through
American,
different moments
South
in our
American,
day, yet all
Asian,
of us are connected by
Australian,
this
and
one
Antarctic
planet
plates
beneath our
were
feet.
squished together
This
with a
very
few
same
others that
Earth
are
has
harder
carried
to
us,
identify today.
and every
The
living
edges of
thing
the
that came
continents
before
are pretty
us,
blurry.
through
The
billions
continents
of
didn't
years
hang
of
out in the same
unimaginable
configuration
change.
forever.
Continents have
They
crashed
shuffled
together and ripped
around.
themselves
For
apart.
example, Laurentia,
Oceans have
an
been
early
born from
version of
gaping
what would
wounds in
become
crust
part of
and
North
have drained away
America,
into memory.
broke off from the main
Climates have
cluster
frozen the world
and took a
solid
little
and
trip
boiled it
around the
under a
globe.
hazy,
It wasn't
alien
alone.
Sunday.
The Baltic
The world
Craton,
we think
now
we know
found
today
in
is
parts
just
of
the most
Europe,
recent
rode
face
along
that our
for a
planet has
while
worn.
until the two
And if you
split
find
up
this slow
somewhere between
exploration of time
1.8 and
soothing
1.6
or
billion
interesting,
years ago.
or just
Around
a
that
nice,
same time,
calming
another chunk
background
of
noise
land
for
called
winding down your
Baltica
day,
joined up with
I'd be
Laurentia.
so grateful if you
Together,
tapped
they
the like
formed a new
button
continent
and maybe
that
even considered
scientists call
subscribing.
Nuna, or Columbia.
It really helps
It
this little
lasted less
corner
than
of calm
300
find its
million
way to other
years
people
before
who could use
breaking
a peaceful
apart.
pause
Some
too.
bits went
I
on to
can
form
promise you,
part of future
this isn't the kind
continents,
of science
while
that's
others
going
got
to jolt you
recycled
awake
back
with
into the planet's
explosions or
molten
jarring
mantle.
facts.
That process of
We're not
creation
racing
and
through a
destruction
textbook
has
tonight.
been happening ever
Instead, we're
since
going to
Earth
stroll.
cooled enough to have a
We'll
solid
notice the
crust.
details, the way
New
you might
land
notice
keeps
the
getting
texture of
made,
leaves
and as
along a
long as
path
there's
or the
plate
smoothness of
tectonics,
stones
it
on
will
a
keep
shore.
getting
We'll
destroyed.
take our
It's
time,
part of a
because
cycle that's
time is
easy to get
exactly what
obsessed
Earth
with.
has had in
We know
abundance,
that Earth's surface
an
is in
almost
constant flux
incomprehensible
because of
amount of it.
fossil evidence.
So,
Scientists have
let's
found
begin with
fossils of
something
marine
familiar.
creatures high up in the Rocky
Pangea.
Mountains. How
When
did they
most of
get
us hear
there?
that name,
They were carried
we
aloft
picture a
by the
single
very same
vast
forces
continent.
that built the Rockies.
We imagine a
The
perfect
land rose
jigsaw
out of the
puzzle,
sea,
where
carrying
all
the
the pieces
fossils
of
with
today's
it.
world
Mountain
fit
building
neatly
continues to this
You've
day.
probably seen the
Parts of the
diagram
Eurasian
where South
plate are
America
crumpling up
snuggles
beneath
up
the
against the
Himalayan
coast of
mountains.
Africa like
One
two
day, the
long-lost
Himalayas
relatives
will be the
finally
site of
reuniting.
ancient fossils.
You might
It's a
picture it as the
humbling
grand
thought.
stage
When
where
we
the
look at the
dinosaurs
grand
had their
sweep
reign,
of geologic
before the
time,
land
we tend to
itself
pick out
fractured
the
and the continents
highlights,
began
the
their
asteroid
long, slow
impact that
drift
killed the
apart.
dinosaurs,
And all of that
the
is true.
emergence of life, the first
Pangea
mammals,
was very real.
the first primates,
It
the
existed
rise
around
of
300
humans.
million years
But in
ago.
reality, Earth's
Colossal
history is full
landmass
of
stretching
subtle
from the North
changes.
Pole to the
It was
South
never
Pole.
one thing for
But here's
long.
the twist,
It cycled
the
through
detail that
tons
often
of
gets overlooked in our
configurations.
school lessons.
Landscapes changed
Pangea
slowly
was not the
and
first time
sometimes
Earth had
pretty
gathered all its
fast.
lands into
About
one.
300
Not
million
even
years
close.
ago, Pangea was
It was simply
surrounded
the
by
most
a
recent.
single ocean
Our
called
planet, you see, has
Pamphilasa.
this incredible
About
long-running
175
habit of
million
recycling
years
itself.
ago,
The
Pangea
ground
began
beneath
to
us
break
isn't solid and
apart,
fixed.
and the Atlantic
It's a
Ocean
restless
started to
mosaic
form.
of tectonic
Then
plates.
things got weird.
These
About
plates shift,
145
pulled
million
and
years
pushed by
ago,
the slow
the Pacific
churning
Ocean
currents
shrank
from the molten mantle
dramatically.
deep
What
below.
happened?
Oceans
Most of it
widen,
turned into rock.
mountains rise,
As the
and are weathered
Americas
down to
moved
dust.
west, they
And over
smashed into
hundreds of
Asia,
millions of
and the
years,
Pacific Ocean
continents
got pinched
drift,
out of
collide,
existence.
and
The
merge into
teethless ocean that
supercontinents,
formed in its
only to
place
break
would
apart and
eventually
begin the
disappear
cycle all
too.
over again.
By 50
This
million
grand
years
cycle has
ago,
happened
the
not
Indian
just once or
subcontinent
twice,
had
but
crashed
several
into
times
Asia,
across Earth's
sealing the
immense
Tethys'
history.
fate.
So,
Earth's not
if
done
Pangea was just
recycling
the
either.
latest chapter,
In 200
what came
million
before
years
it?
or so,
What
Australia will crash into Southeast Asia, the Pacific Ocean will vanish as we know it, and life will never be the same. In fact, the exact nature of the next supercontinent is up for debate among geologists. They argue over whether the next one will be called Amasya, which would include Africa, Asia, and Europe, or maybe Eurasia, which would include the same three continents, plus the Americas. A lot of the disagreement comes down to how fast the plates are moving, which is a hard thing to predict. Continental collisions aren't like car crashes. The continents don't slam into each other in an instant. They move toward each other over millions of years, and sometimes they get stuck and wiggle around a little. The end result, whatever it ends up being called, will look nothing like Pangea. New oceans will form, and the climate will change in ways we can't even imagine yet. It's hard to wrap our heads around the idea of continents drifting on a constantly shifting surface. Their outlines change in our lifetimes. The idea that we have a solid understanding of geography can be comforting. We draw borders on maps and think of countries as permanent fixtures, but they're
Evidence
not.
is erased by
It's hard to
relentless
predict
erosion.
where countries will be in
Fossils
100
from these early
years,
times
let
are
alone
incredibly
100
rare.
million.
So much
There
of
are
what we know
signs
about
that tell us
pre-Pangean
that the
Earth
world
comes
is
not from
changing.
tidy,
Sea
clear-cut
levels are
evidence,
rising,
but from
weather
hints.
patterns are shifting, and
Fragments of
glaciers are
ancient
melting.
rocks
But
scattered
on a
across modern
geologic
continents.
timescale,
Their
those
stories
changes
jumbled.
are a blink,
Faint
and you'll miss
magnetic
them.
traces
The
frozen
only
inside
certainty
tiny
is that the
crystals,
continents will
acting
continue
like
to
microscopic
shapeshift.
compasses pointing
Over
to a
billions of
long-gone North
years,
Pole.
they've taught us that they
Chemical
can do
whispers
anything,
hidden in
and
ancient
on that
minerals.
note, our
Piecing
journey
it all
through
together
Earth's
is a
ancient
monumental
landscapes
act
has
of
come to an
geological
end.
detective work.
I hope you enjoyed
bit
our
by
quiet
bit,
walk back in
scientists
time,
have
back before
reconstructed enough to
Pangea,
give us
back
glimpses
before
of those
dinosaurs,
forgotten worlds.
back before the world was
One of those
ours in any
glimpses
way that
reveals a
we know.
supercontinent
I hope
called
you felt a
Rodinia,
sense of peace
which
in the
existed
vastness
about
of it all,
1.1
a reminder
billion
that
years
even
ago.
in our frenetic
Before
modern
Rodinia,
world,
there was
even
Numa,
when we're caught
also
up in the
known as
rush of
Columbia,
every day,
a giant
life, we are
landmass
part
more
of
than
something much
1.5
bigger.
billion years old.
Remember the
Even
continents,
earlier there was
those
Canola,
ancient
and farther
recyclers,
back
those
still,
eternal
a tiny
storytellers etched in
proto-continent
stone.
called Ur,
Their silent
which may have
symphony
been
has
one of the
played out
first
for billions of
recognizable
years,
continents.
shaping life
These
and
names might sound like
landscapes.
they belong in a
Tonight,
fantasy
I invite
novel,
you to carry this
but they are
feeling
very
of
real
grounded
markers in the
perspective
story
with
of our
you
planet.
as you step back
Just
into
think
the
about
rhythm
that
of
for a
your
moment.
day. May
When
it serve
Pangea
as a quiet
existed,
hum beneath
the
the
world already had
busyness, a
forests,
gentle
rivers,
echo in the chaos.
sprawling deserts,
Whether you're nestled under a
reptiles,
blanket
and
or
insects.
sipping your morning tea,
But when
wherever
Rodinia
you are,
existed,
whatever
there were no
tomorrow
trees,
brings,
no
know
animals
that
on
you're a
land,
part of a
no
story
flowers.
that's always
The world was
unfolding,
almost alien.
even when it seems
If
the
you go back
pages are
further to
turning
Nuna
too
and
fast.
Kenneland,
Thank you for
life was
joining me
even
on this
simpler,
episode of
mostly
Just About
microbial,
Earth. If
clinging
you
to
found
dusty
solace in
shorelines
our
or
journey
floating
through
in
Earth's
ancient
deep
seas.
past,
To
please
imagine
consider
Earth before
tapping the
Pangea
like button and
is to imagine a
subscribing.
world where the
Your
continents
engagement
themselves
helps
were the
spread
main
the warmth
characters,
of calm
drifting
amidst
and
the
colliding
digital
on a
din.
stage almost
As
empty of
always,
the life
I
we're
wish
so
you a
familiar with.
universe filled with
And yet,
curiosity
though the
and a
biological
cosmos
stage
full
was
of
bare,
contentment.
the
Until
geological
next time,
drama was
keep
immense.
looking up and keep
There were
seeking the
volcanic
quiet
eruptions
corners
that
of the
lasted for
universe that bring
millions
you
of years.
peace. Good night,
Oceans that
everyone.
swallowed whole
The Earth we
continents,
live on
and
feels
ice sheets that
unchanging.
may have stretched
Maybe
from the
that's why we
poles
name
all the way to the
hurricanes
equator
after
in an
people
event
we
known as
dislike.
Snowball
We
Earth.
can imagine those
Every
names
collision of
drifting off the
continents
top of
reshaped
our
not just
heads
the
and
land,
somehow
but
sticking
the
to the sides
atmosphere,
of buildings.
the oceans,
Can't imagine
and
anything
eventually,
changing in
the
our
very course of
lifetimes.
life itself.
Yet the ground beneath our
Sometimes when we
feet
think
is
about
always
history,
moving.
our
Not
minds go
enough
back
to
a
make
few
you dizzy,
thousand years,
but just
or
enough
maybe
to
to the time of
rearrange
the
the world
dinosaurs,
in
and it
ways that
feels
are beyond
vast.
human perception.
But Earth's
We're
deep
sitting
past
comfortably
stretches
on a
so far
single
beyond
frame
that.
of a film
All of
stretching
human
back
history is
billions
just
of
a blink of
years.
an eye compared
Given
to
enough
these
time,
cycles of
our world can
supercontinents.
change a lot.
Even the
There are
dinosaurs,
entire
with their
branches of
impressive
science dedicated
1.65
to studying
million
this
year reign,
change.
lived and died
Climatology,
long
geology,
after Rodinia had
evolutionary
already
biology,
broken apart.
ecology,
It makes you
but none
wonder,
can appreciate the
what did
change
Earth
quite
feel
like
like back
cosmology. If you
What
take a
did the
long
sky
view
look
of the
like without
cosmos,
birds?
the Earth isn't just
What
a
did the
bit of
land
space
smell
rock
like without
hurtling
flowers?
around the sun.
What did
It's a
silence
blip in
sound
an
like
epic
without the
saga
buzz of
that
insects or
stretches
the
from the
calls
Big
of
Bang
animals?
to forever.
Though we can't
And
truly
Earth
know,
isn't just going
we
around
can
the
piece
sun.
together enough
The
to
sun is
imagine.
going around the
And so,
galaxy.
as we
Our
wander
solar
tonight
system
through
is
the
dancing with
landscapes that came
others
before
in the
Pangea,
Orion arm of the
let's
Milky
keep in
Way,
mind that our
and the
planet has
Milky
never
Way
been
itself
static.
is spiraling
It's
around
always
the
been in
galactic
motion,
core. We're
always
spinning and
changing,
twirling through the
always
universe at
reshaping
8
itself in
kilometers per
cycles so
second,
vast we can
orbiting
barely
a
wrap our
star
minds
that in
around
4
them.
billion years will
This isn't
expand
just a
and
story
engulf
of
the
rocks
Earth.
and tectonic
Just
plates.
knowing this makes
It's the
our
story
lives
of the
feel
planet
both very
itself.
small and
A
also
planet that has worn many
inconsequential.
faces,
In
some
fact,
familiar,
our little blue
some
dot
utterly
is doing
alien,
better than most
long
planets
before
in the
we ever
Milky
arrived
Way.
to give them
According
names.
to NASA,
If you look at a modern world
2/3
map
of the
for long
stars
enough,
in the
you can
galaxy
almost
have
start to
planets,
feel alive.
but only a
The
fraction of those
continents don't
planets
seem
are
like they're
suitable for
frozen in
life.
place,
We tend to
but
think
more
of
like they've been
ourselves as
caught
privileged
mid-step in
to
a
live on
very,
this
very
perfect
long
little
dance.
sphere, but in
South
truth,
America
we're
leans
lucky
in
to be
toward
here at
Africa,
all. The
like
Earth
an
has
old
been
friend
struck
who
by
once lived next
asteroids.
door.
Continents have crashed
Australia
into one
looks as if
another.
it's trying to slip
Volcanic
quietly out
eruptions
the
have
back,
blanketed the
heading
surface
north.
in lava.
And
Yet
Antarctica
life has
sits at the bottom of
survived,
the globe
and
like
we're
a guest
really
who
lucky to
wandered
be
too far
alive at
south
this
at a party
particular
and
moment
decided
in
to just stay
history,
there.
because the
Of
Earth
course,
has never been
the map
still for
itself is
long.
still,
Let's go
but what
back
it
to
shows
that
us
map
is only
again. The Earth is in constant motion. It seems like the whole thing is one great big puzzle whose pieces twist and turn across the surface of the planet. At first glance, it looks as though the Earth is being held together by these well-known continents, but it's really the opposite. The Earth holds the continents in place. Our planet is made of layers, including a solid core, an outer core, a mantle, and the crust. The crust and the uppermost part of the mantle together make up the lithosphere, which is broken into at least 7 large slabs called tectonic plates. These plates float on the semi-molten asthenosphere below, and they glide across it. The heat inside the Earth generates convection currents in the asthenosphere. These currents drag the plates along with them. On average, they move about 2 centimeters per year, about as fast as your fingernails grow. Most of the movement happens at the boundaries between plates. Some of these boundaries are diverging, meaning they're moving apart. At these boundaries, magma from the mantle rises up and creates new crust. Other boundaries boundaries are converging, meaning they're colliding. Where two continental plates collide, neither plate moves much. Instead, one plate is usually pushed under the other, sliding into the mantle. This is called subduction. Subduction zones often produce volcanoes, as seen along the western edge of South America, which marks the boundary between the Nazca Plate and the Pacific Plate. Friction slows the plates down, and this causes earthquakes. Transform boundaries, on the other hand, are sliding horizontally past one another. The San Andreas Fault in California is an example of a transformed boundary, because the Pacific Plate is moving roughly southwest, while the North American Plate is moving northwest. The two plates rub against each other, and this generates a tremendous amount of friction, causing major earthquakes when the stress becomes too great. Now, when we talk about the continents moving, we're mostly talking about the relatively thin outermost layer of the Earth's structure, the crust. And the Earth's crust comes in two varieties, oceanic crust and continental crust. Oceanic crust is thinner and denser than continental crust, so when the two types meet at a converging boundary, the oceanic crust dives under the continental crust. When an oceanic plate collides with a continental plate, the denser oceanic crust bends and sinks down into the mantle. This bending is driven by the high pressure and temperature at the boundary. The slab of oceanic crust melts as it sinks lower and lower into the Earth. The Earth's interior is hot enough to melt rock, but the pressure is also high enough to keep the rock rigid. Deep in the mantle, temperatures reach 4,000 degrees Celsius, but pressures reach 3.5 gigapascals. This is the zone where the oceanic crust actually melts, turning back into magma. The magma then begins to rise toward the surface. As it rises, the pressure decreases and the temperature drops. The magma solidifies into new rock, creating mountain chains of continental crust. This process of creation and destruction of the oceanic crust is what makes the seafloor so young. On average, the oldest seafloor is only about 200 million years old. Continental crust, on the other hand, can be billions of years old. It's so much older than the seafloor because it's recycled more slowly. Continental crust is less dense than oceanic crust, so it doesn't sink into the mantle as easily. This means that the continental crust is not destroyed as quickly as the oceanic crust. Instead, it's often buried under younger layers of sediment or rock. The cycle of creation and destruction of the Earth's crust is one of the most fascinating aspects of our planet. New crust is created at mid-ocean ridges and destroyed at deep ocean trenches. And this cycle is constantly reshaping the Earth's surface. If you zoom out enough, you can see that the Earth is covered in scars from this reshaping. Major mountain ranges like the Andes, the Alps, and the Himalayas mark where tectonic plates have collided. Deep ocean trenches, like the Mariana Trench, the deepest part of the Earth's oceans, show where one plate is sinking beneath another, and vast stretches of flat land, such as the Great Plains in North America, tell the story of plates sliding past one another. All of these features are the result of the constant motion of the Earth's crust. The Earth's crust is always changing, but some changes are more dramatic than others. For example, the splitting of the supercontinent Pangea about 175 million years ago. This event, known as the breakup of Pangea, had a profound impact on the Earth's crust. As the supercontinent split apart, new ocean basins formed, mountain ranges rose, and continents moved to their present positions. This dramatic reshaping of the Earth's crust continues to affect our planet today. For example, the breakup of Pangea led to the formation of the Atlantic Ocean, which has played a major role in shaping the climates of the continents. It also led to the isolation of populations of plants and animals, which has resulted in the diversity of life that we see today. The effects of the breakup of Pangea can be seen in the rocks and sediments of the Earth's crust. For example, the Mid-Atlantic Ridge, a mountain range that runs through the middle of the Atlantic Ocean, was formed as the two plates that make up the seafloor spread apart. This mountain range is a record of the movement of the Earth's crust since the breakup of Pangea. In addition to the movement of the Earth's crust, the Earth's interior is also constantly changing. The heat from the Earth's core creates convection currents in the mantle, which drive the movement of the crust. These convection currents also cause the rock in the mantle to flow, and that flow can change the shape of the Earth's crust. For example, the African continent is currently moving towards the Eurasian continent. This movement is caused by the flow of the mantle below the crust, and is likely to continue for millions of years to come. The Earth's crust is also constantly being reshaped by volcanic activity. Volcanoes form when magma from the Earth's interior erupts onto the surface. This magma can be molten rock from the mantle or melted rock from the Earth's crust that has been pushed deep into the mantle and brought back to the surface. Volcanic activity can create new landmasses and can also reshape existing landmasses. Overall, the Earth's crust is in a constant state of flux. The movement of the Earth's plates, the flow of the mantle, volcanic activity, all of these factors are constantly reshaping our planet. While some changes are subtle and occur over millions of years, others are dramatic and can occur over a matter of days. The Earth's crust is a dynamic and ever-changing feature of our planet, and its story is an essential part of the story of the Earth as a whole. If Pangea is the supercontinent most of us know from school, then Rodinia is the one that hides in the deep background of Earth's story. It's a name that rarely comes up outside of geology classrooms, but it represents one of the most important and mysterious chapters in our planet's history. It existed more than 1 billion years ago, long before animals, long before forests, long before life had even figured out how to build shells or skeletons, and yet it gathered nearly all of Earth's land into a single, massive cluster, shaping the planet in ways that would echo for hundreds of millions of years. Rodinia's name comes from a Russian word meaning to give birth or the motherland, which feels incredibly appropriate because, in many ways, it was a birthplace. It was a time of immense geological and environmental change that set the stage for the more complex world that would come later. It formed about 1.1 billion years ago, during a time when Earth was already more than 3 billion years old. Continents had been colliding and breaking apart since the planet first cooled enough to form a solid crust. But Rodinia was one of the largest and most stable unions of land the world had yet seen. Of course, no one was around to see it. There were no animals to wander across its vast, barren surfaces, no trees to mark the passing of seasons, no flowers to bloom and fade. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was no lushness anywhere. There was only the raw reality of land meeting sky. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow rusty-colored seas and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow rusty-colored seas and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas and skies that were tinted by the chemistry of an atmosphere, still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when we try to picture Rodinia, we have to strip away everything we find familiar about a living landscape. There were no birds in the sky, no grass underfoot, no insects buzzing through the air. There was only bare rock, massive volcanic eruptions, shallow, rusty-colored seas, and skies that were tinted by the chemistry of an atmosphere still adjusting to the slow rise of oxygen. So when this world is so alien that we might not recognize any of it. You might have thought our previous episode on the supercontinent Rodinia was way back in deep time, but we're about to go even further. We're now talking 4 billion years ago, or even older. We don't know exactly how old, because honestly, nobody knows what was going on. Back then, the simplest of our modern concepts, like continents and oceans, didn't exist yet. Earth hadn't fully cooled. Its surface was still molten and bubbling in places. The atmosphere had just a little oxygen in it, maybe enough to make breathing really hard, but not enough to support flight. And all life was concentrated in the seas, and probably pretty simple to boot. Those conditions sound miserable. So how can we talk about a forgotten world like that? It's actually deceptively simple. We study them all the time. Geologists learn about the history of our planet by looking at the oldest rocks that they can find. The problem is that a lot of those old rocks aren't really that old. Most of the Earth's crust, the solid outer layer of the planet, is between 400 million and 2 billion years old. Anything older than that has been so thoroughly recycled by the constant churning of plate tectonics that it's gone. Or has it? Yes, most of the Earth's oldest rocks are between 400 million and 2 billion years old. but there are a few that are 3 billion years old, and there are even a handful of others that are more than 4 billion years old. What's more, these aren't mere fragments of rock, but entire piles of rock, hundreds of meters thick. Some of them are even parts of mountain ranges. And yes, they tell a story of volcanic activity on early Earth, but they also suggest the presence of stable continents. In fact, their age suggests that the continents might have been around for quite a while already. By 4 billion years ago, Earth had grown to almost its present size, but it looked nothing like the world we know. The continents weren't assembled the way they are now. Instead, they were a bunch of scraps floating in a big primordial sea. And it's here that we must tread carefully. Scientists have struggled to figure out how this sea, sometimes called Nile Sea, fits into the grand scheme of Earth's history. Why does that matter? Because it could contain the answer to one of the biggest questions in all of geology, namely, when did dry land appear on Earth? That's a question that relates directly to the origin of life. Because life eventually arose on land, both on our planet and almost certainly on any other rocky world in the universe. Without land, there wouldn't be rivers and lakes and forests and mountains and soil. All life would be doomed to the oceans forever. So let's talk about this strange, hot, inhospitable world and what we think happened in it. Let's do some prehistoric geology. We're going to need to get real technical here and start talking about half-lives. Okay, cool. Good. Now what? Good. Cool. Glad you're still with me. But you don't actually need to understand any of that math. You just need to understand that radioactive decay works like clockwork. Every atom of every element has a half-life. For example, the half-life of uranium is about 700 million years. Every 700 million years, half of all the uranium atoms in the universe will turn into thorium. Thorium then has its own half-life and turns into something else. And that's why we use the element hafnium to date rocks. Hafnium doesn't occur naturally. It's produced by the radioactive decay of uranium. So if you know the half-life of uranium and you see a rock full of hafnium, you can calculate backwards to find out how old the rock is. Well, that's all fine and good, but the problem with dating old rocks is that their VA had a lot of time to leak away their hafnium. See, hafnium is volatile. It tends to evaporate over time. And as a result, most rocks, older than 1 billion years or so, have lost essentially all their hafnium. It's a problem unless you have a rock that's younger than other nearby rocks, but still old enough that its hafnium levels have dropped below detection limits. Then you can use something called isotope dilution to get an approximate date. That's what researchers did with a 4.4 billion-year-old pile of granite in Greenland called Isua, and the results were controversial. Isua turned out to be slightly younger than other rocks in the region, meaning it could have kept some of its original hafnium. Isotope dilution dating suggested that it crystallized from magma 4.26 billion years ago, possibly even 4.3 billion years ago. If that's right, it would mean that there were islands on Earth, at a time when the rest of the planet was still largely a global magma sea. But if that's true, then why is Isua so tiny? Granites like this usually form when huge batches of magma cool, but Isua is only a few hundred meters across. It looks more like a pile of volcanic rubble. And if Earth was covered in magma at the time, where did the magma come from? Well, one team of scientists proposed that Isua was actually a meteorite, a fragment of another body that cooled in space and crashed into Earth's magma sea. But that raises another question. If there was dry land elsewhere in the solar system so early in its history, why isn't it there still? Wouldn't that be a huge clue to figuring out how life began? Meteorites don't preserve well. They tend to get lost in the shuffle of Earth's recycling geology. But the bigger problem is that even if we accepted the meteorite hypothesis, it doesn't really answer our question. It just pushes the question back a step. Where did the meteorite come from? So for now, we're left with this weird, hot, inhospitable world and one tiny pile of granite that looks utterly out of place. It's a place that seems so unlike our own. Could life have arisen in such a world? Perhaps, but not easily. The leading hypothesis among geologists is that habitable environments did exist on early Earth, but only in cracks and crevices. Water vapor escaping from the deep ocean could have mixed with carbon dioxide in the atmosphere to form weak acids, which could then weather the rocks and form pools of liquid water in the nooks and crannies of the continents. In those pools, life could have arisen and eventually made its way onto land. In fact, evidence suggests that the process of weathering rocks might have played a key role in stabilizing Earth's early atmosphere and making it hospitable to life. But of course, that was billions of years after the formation of the solar system, and we're really not sure exactly how long it took for continents to form. If they formed quickly, the path to habitability would have been quicker. If they formed slowly, it could have taken a few billion years. We can't say for sure, because we can't actually look that far back. The best we can do is piece together the hints and clues preserved in the fossil record, and sometimes those clues point in different directions. Other isotopic analyses of Greenland rocks have suggested that Earth's surface was entirely molten at 4.5 billion years ago, meaning that any early continents were totally lost to the magma sea. Other analyses have put the age of continents at between 4.2 and 4.4 billion years old, a surprisingly recent date for Earth's history. Even within the scientific community, there's no consensus on when dry land first emerged, but the implications of the answer are huge. How fast Earth cooled from a molten sphere would have had a major influence on the development of life. A longer cooling time would mean more time for life to adapt to a harsh environment and gradually transform it into something more hospitable. Meanwhile, a shorter cooling time would mean a much more hostile world, where life had a much harder time getting started. But whichever way it shakes out, one thing is certain, that ancient world was nothing like our own. The sky was thick with debris from the late heavy bombardment, volcanoes dominated the landscape, and gigantic meteorites rained down from the sky. The continents themselves would have been barren, stark and lifeless, and yet life still found a way to cling to existence in the most unlikely of places. It wasn't until the formation of Rodinia, some 1.5 billion years ago, that Earth began to resemble the world we know today. Our journey is now complete, from the hazy beginnings of Nuna to the fractured world of Rodinia and beyond. Each continent holds clues to the past, whispers of a history that stretches back billions of years. The next time you gaze upon a mountain range or a winding river, remember that you're re-witnessing features sculpted by forces that have been at work for tens of billions of years. And as we continue to explore the history of our planet, who knows what other secrets we'll uncover? Maybe we'll even discover signs of life, perhaps in the form of fossils or chemical signatures, hidden within the ancient rocks that tell the story of Earth's first forgotten worlds. But for now, their legacy lives on in the very land we walk upon, a testament to the endless cycles of creation and destruction that have shaped our home.
When all, or most, of Earth's continents gather into one, we call it a supercontinent. And like a slow-motion heartbeat, the cycle repeats. Supercontinents form, they exist for a time, and then they inevitably break apart again, only to begin the long journey toward reforming in a new configuration. Pangea is the most famous example, but it was not the first, and it will not be the last. Before it came, Rodinia, Nuna, and Kenoland. Each had its own lifespan, its own breakup, and its own legacy. The timescale for one full cycle is vast, typically around 400 to 600 million years. But why does this cycle even happen? The answer lies in the mechanics of heat and rock. When a supercontinent forms, it acts like a giant insulating blanket over the mantle. Heat from Earth's core gets trapped beneath it, unable to escape easily. Over millions of years, that trapped heat builds up, weakening the continental crust above. Eventually, the pressure becomes too much. Rifting begins, cracks appear, and the land splits apart. New ocean basins open between the fragments, pushing the continents away from one another. But the Earth is a sphere. As the continents drift around the globe, the older oceans on the opposite side of the planet begin to close. Eventually, the scattered pieces are drawn back together. Another supercontinent forms, and the cycle begins anew. This pattern affects far more than just geography. It is a primary driver of climate, ocean circulation, and even the course of life itself. When continents cluster together, the interior regions tend to become extremely dry and seasonal, far from the moderating influence of the sea. When they disperse, shallow seas spread along their margins, creating fertile, stable environments where life can flourish. The breakup of Rodinia, for example, may have triggered the global snowball Earth ice ages. Mountain building is also tied to the cycle. Every time continents collide, mountains rise. These new mountain ranges alter wind and rainfall patterns, and as they erode, They deliver a flood of nutrients into the oceans, fueling biological productivity. In this way, the supercontinent cycle intimately links the living world with the non-living in a constant feedback system that has shaped Earth's history for billions of years. And this story doesn't just stop in the past. We are living within a cycle right now. The continents are currently in a dispersed phase, moving slowly toward the next assembly. The Atlantic Ocean is widening as North America and Europe drift apart. The Pacific Ocean is shrinking as plates are subducted along its famous Ring of Fire. In roughly 200 to 300 million years, it's likely that a new supercontinent will form. Scientists have even given it a nickname, Pangea Proxima. The cycle continues, as it always has. Thinking about this puts our own time into a humbling perspective. Human civilizations rise and fall in a few thousand years. A species might last for a few million. Yet the continents move on timescales of hundreds of millions of years. Our entire history fits within a tiny sliver of this immense planetary rhythm. It is the recurring pattern that ties all the chapters of Earth's story together. And as we follow this rhythm, it naturally leads us to consider not just the continents themselves, but the vast, vanished oceans that once separated them. When we talk about continents moving and colliding, it's easy to focus on the land itself, those giant puzzle pieces that drift and rearrange across the globe. But for most of Earth's history, the true stage, the place where the real action was happening, was the oceans. Long before the first forests grew, long before any animal walked on land, the seas ruled everything. They were the cradle of life, the great regulator of the planet's climate, and the vast, dynamic reservoir that covered nearly the entire world. To understand Earth before Pangea, you have to imagine not just the wandering continents, but the immense, vanished oceans that spread between them, shaping every single aspect of the planet's story. Today, our planet is about 70% ocean. But in the deep past, that percentage was often even higher. The continents were smaller and more scattered, and they were always surrounded by water. Those ancient oceans weren't static either. They opened and closed as the continents drifted. One ancient sea would vanish as two land masses collided, its waters squeezed out and its floor crumpled into mountains, while somewhere else, a new ocean basin would be born as the land rifted apart. The history of our planet is written in these vanished oceans, and though we can no longer sail them, their traces linger in the rocks right beneath our feet. One of the most significant of these ancient oceans was called the Iapetus Ocean. It opened roughly 600 million years ago, separating the land masses that would later become North America, Europe, and parts of South America. For more than 200 million years, the Iapetus stretched wide, hosting a rich and expanding array of early marine life. Trilobites scuttled along its seafloor, and the first primitive fish appeared in its shallows. Eventually, the Iapetus Ocean closed as the continents drifted back together to help form Pangea. Today, the Appalachian Mountains in North America and the Caledonian Mountains in Scotland and Norway mark the geological scar of that closure. They are the eroded, mountainous reminders of an ocean that no longer exists. But the Iapetus was far from the first. Before it, there were oceans with names like Merovia, which is thought to have surrounded the supercontinent Rodinia about 1 billion years ago, a global ocean stretching almost uninterrupted around that single landmass. Later, the ocean of Panthalassa would dominate the world, surrounding Pangea and covering nearly 3/4 of the globe. Each of these seas had its own lifespan, opening with rifts, thriving for millions of years, and then vanishing as the continents collided once again. Imagine standing on the shore of one of those vanished oceans. The waves would look familiar, the sound of the surf would be the same, but everything else would be utterly alien. The air might carry a different mix of gases, the sky might have a slightly different tint. The shoreline itself would be barren, with no grass, no trees, and no animals leaving tracks in the sand. All the life was in the water. This was especially true during the Cambrian period, starting about 541 million years ago, when, in a geological blink of an eye, life diversified at a pace never seen before or since, an event we call the Cambrian explosion. The seas suddenly went from being populated mostly by simple, soft-bodied organisms to hosting a bewildering menagerie of creatures with shells, spines, eyes, and complex body parts. Strange arthropods like the trilobites were everywhere, but there were also predators like Anomalocaris, which looked like nothing alive today, with large grasping claws at its front and a circular mouth lined with sharp plates. The oceans were the planet's first great laboratory, where evolution experimented with countless forms, many of which would eventually vanish. The oceans also played the central role in regulating Earth's climate. Currents carried heat from the equator to the poles, distributing energy across the planet. When supercontinents formed, they blocked those currents, changing the patterns of heat and moisture. When they broke apart, new circulation systems developed. These shifts could trigger ice ages or intense greenhouse periods, creating the environmental challenges that drove evolution forward. To call the oceans the rulers of early Earth is no exaggeration. They were the setting for nearly everything that mattered. And from those ancient seas came the life that eventually crawled onto land, looked up at the sky, and began to wonder about the strange atmospheres that hung over these alien worlds. When we think about Earth's distant past, we often picture the land or the seas because they feel solid and tangible. But just as important to the story is the invisible world of the air that surrounded it all. The sky has not always been the familiar, friendly blue that we know today. The mix of gases we breathe, the quality of the light, even the presence of clouds in the forms we recognize. These are the results of billions of years of profound change. If you were somehow able to stand on Earth in its different ancient eras, the air itself would have felt, smelled, and looked completely different. The atmosphere has been a central player in the drama of Earth's history, shaping its climate, guiding the course of evolution, and even determining whether complex life could exist at all. More than 4 billion years ago, Earth's earliest atmosphere was a thin veil of hydrogen and helium, gases left over from the formation of the solar system. But these light gases quickly escaped into space. What replaced them came from within. For hundreds of millions of years, volcanoes vented a constant stream of gases: water vapor, carbon dioxide, nitrogen, and a significant amount of methane. This secondary atmosphere was heavy, hazy, and completely hostile to life as we know it. Crucially, it contained almost no free oxygen. With so much methane, a potent greenhouse gas, the early sky may have had a hazy, orange or reddish tint, similar to what we see on Saturn's moon, Titan, today. This methane blanket was essential for keeping the young Earth warm. At the time, the sun was significantly dimmer, a phenomenon known as the faint young sun paradox. Without a powerful greenhouse effect, our planet should have frozen solid. Instead, the methane-rich atmosphere trapped enough heat to keep water liquid, allowing the first simple life to emerge in the oceans. But then, as we've seen, something happened that changed everything. Around 2.4 billion years ago, photosynthetic cyanobacteria began releasing vast amounts of oxygen. This great oxidation event completely remade the sky. As oxygen levels rose, it reacted with the methane, destroying it and weakening the greenhouse effect. The planet cooled dramatically, perhaps triggering the first global ice ages. For the anaerobic life that had thrived in the old world, oxygen was a poison, and this was a catastrophe. But for the future of life, it was the foundation. The rising oxygen eventually formed the ozone layer, a protective shield in the upper atmosphere that absorbs harmful ultraviolet radiation from the sunday. Without that shield, life would have never been able to leave the safety of the water and colonize the land. The sky itself, by gaining that thin layer of ozone, became a guardian. And so here we are, back in our own time. After wandering through faces of the Earth that are long, long gone, we've followed continents as they drifted like lonely ships across vanished oceans. We've walked among the first forests, where giant insects buzzed in the deep shadows. We've watched the slow, inevitable march of lands gathering into the supercontinent Pangea. The ground beneath us, the air we breathe, the very map we know, all of it is temporary, just a single moment in an ancient, unbroken rhythm. If you've stayed with me through this quiet journey, I thank you. It's strange to think that something as familiar as the planet beneath our feet can also be so fleeting, that every coastline we know is just passing through. But that strangeness is part of the wonder. When you step outside tomorrow, maybe take a second to look at the sky, or touch the ground, or listen to the wind. They are all carrying pieces of that deeper history stories, older than forests, older than animals, older than Pangea itself. And if you found this gentle walk through time soothing or interesting, or maybe even a little bit sleepworthy, you can always join me again. There are still so many more questions to ask, more forgotten worlds to visit, more pieces of Earth's story waiting quietly to be told. Until next time, wherever you are, Whatever hour it may be, may you rest easy, knowing that even in its endless changes, the earth keeps turning, the continents keep drifting, and the story goes on.